Well, you came back. That's the good news. The bad news? There is no bad news. It's all good news. We're going to be using those properties of logarithms that we learned. And a quick recap. When you multiply logs, you may add them. When you divide a log, you may subtract them. And when you take a log raised to a power, you may multiply it. Well, let's use all of that information to figure out certain equations. So here we go. Now, it's log base 7 on both sides, which is a clue. That's a key to help us here. So we got a good base, so we're fine. As long as we can set these sides equal to each other, we're good. The problem is we have the 2/3 here out in front. It has to be log base 7 of n equals log base 7 of something. Well, what can I do with that 2/3? Right, because I'm multiplying it, I can make it a power. See, it works both ways, that rule. A power can be brought down to be multiplied, or it can be brought up. So now, since I just have log base 7 on both sides, I can now just set these equal to each other. And n equals 8 to the 2/3. 2/3 power. Remember, the 3 is the denominator. So the cube root of 8 is 2. 2 squared is 4. So we'll start out. Of course, they're going to get a little bit trickier, but we'll keep going from now. See what happens. All right. So I got logs. Log, log, log. I got 3 of them, all base 6, which is good. The problem is, these are being added together. So what do? Well, that property with multiplication. If you add the logs, it means you're also multiplying those numbers. So x times 9 equals log base 6 of 54. And now, since we've done it, we've put a log and a log individually on each side. We can set what those logs are equal to each other together. So 9 times x, or x times 9, I'm just going to write it as 9x, 54. Divide both sides by 9. So it's 6. Now we should, and I didn't do on this problem here, I forgot, but it worked out okay. We should make sure our answer works. Because remember, the only danger we have, you cannot take the log of a negative number. So n can't be negative. Well, it's not. It's 4. It's okay. X cannot be negative. Well, it's a 6. So it's okay. Let's just keep that in mind. All log base 8, that's good. We're subtracting. And if you subtract the logs, that means you can divide them. Excellent. Log 8, log 8. So now we can set these two equal to each other. So 48 over w equals 4. 48 divided by what would give you 4? It's 12. Will 12 work? W has to be positive, and 12 is positive, so we're good. All right, here. So we've got a few things going on. We're adding and subtracting. Now remember, this is one term being added. There's no property. Be careful. Log base 9 of 3u plus 14 is not log base 9 of 3u plus log base 9 of 14. It's only when you multiply. So be careful. But we are subtracting these. And when you subtract two logs, what does that mean? It means you can divide them. So this is what you end up with. Over 5 equals log base 9 of 2u. So there we've done it. We've set the log base 9 equal to the log base 9. Those look like a's, but they're supposed to be 9s. So I can set their expressions equal to each other. Just got to do a little algebra. Multiply both sides by 5. Take it over here. I'm going to subtract 3 from both sides. Divide by 7. Put the u first because I always tend to do it that way. U equals 2. Is 2 okay? Well, 2 makes that positive, so we're fine. And 3 times 2 plus 14 is positive, so we're fine. These aren't so bad. Okay. And of course, you know, I say that and then something like this happens. So if I'm adding them, it means I can multiply these logs. And I get a single logarithm expression on both sides. Okay, and that's key. Because some people will look at this and say, oh, a plus 3 plus a plus 2 should equal 6. No, you can't do the logs separately. The logs have to be together as one term. But now that I have a log on both sides, I can now set these equal to each other. Alright, so I'm multiplying these. So I'll do a little foiling. A times A times 2, 3 times A, 3 times 2. We'll combine like terms. I don't know how I change that to a 0. So here's my equation. Now I've got a quadratic, which means I could potentially have two answers. I have to set it equal to 0 when you do a quadratic. That's the best way to do it. That's the only way you can factor. So I'm going to subtract 6 from both sides. Well, 6 minus 6 is 0. So I will be factoring out an A. So my two answers are 0 and negative 5. I do have to check. If I plug 0 in, I get 0 plus 3, 0 plus 2. There's okay, those are positive. I put in negative 5. Negative 5 plus 3 is negative 2. These can't be negative. Therefore, this answer is good, except there's no negative 5. A can only equal 0. Negative 5 will not work. Okay. Similar, we're subtracting. Now if we subtract, that means we divide. So we've written them as single bases of logs on both sides, or single logs on both sides. So r plus 4 over r equals r plus 1. All right. Well, let's multiply both sides by r. R squared plus r. All right, let's take this equation up here. It's a quadratic, I can tell. Of course I can tell it's a square. So I'm going to set it equal to 0. I'm going to subtract r from both sides. Now you could answer it from here. However, let's subtract 4 from both sides. So I want to get us into the factoring mode. R squared minus 4 equals 0. And if you factor that, it's r plus 2 times r minus 2. Scoot it down a smidge. Gives me the two potential answers of negative 2 and positive 2. Now we look over up here. Positive 2 is okay, because 2 plus 4 is 6, 2 plus 1 is 3, 2 is okay. Negative 2. Negative 2 plus 4 is positive 2. That's okay. Oh, here's our trouble. Negative 2 plus 1 is negative 1. Oh well. Sorry, negative 2. You may not be a part of the answer. We have kicked you out of the party. I'm sorry. Feel a little mean doing that, but if I let you equal negative 2, then you just make everything not exist. And no, we can't have that. All right. The little difference with this problem is that we don't have a log on this side. Now, can we subtract a log? Yeah, you can, but then you have a 1 minus log. It doesn't work. So let's combine this like we normally would. If you're adding, then that means we can multiply these. Right, these are all together as one big one. Now, if you see, we're okay here, Because do you remember that property we did in the last section? If I have a log base 8, I can say that n minus 3 times n plus 4 equals the base of 8 to the first power. That's those definition of logs that we learned in the previous chapter. On the previous sections, I'm sorry. So let's multiply this out. We're going to have a quadratic again. N times n is n squared plus 4n minus 3n minus 12 equals 8. Now because it's a quadratic, well, I'll simplify it first, or combine like terms first. So I've got to set this equal to 0. So I'll subtract 8 from both sides. I'm going to get n squared plus n minus 20 equals 0. Well, what two numbers will multiply to be 20 and add to be 1? Right. So my two potential answers are negative 5 and 4. Let's test them. Negative 5 minus 3 is negative 8. That's not good. Just right away, that's no good. Will 4 be okay? 4 minus 3 is 1. Okay, just good enough. And 4 plus 4 is 8. So 4 remains. Sorry, negative 5. You make things not exist, so you got to go. All right, a couple more here. Same idea as the last problem. I got this minus 6 here. There's no log with it. Oh boy, there's lots to do here. Let's first things first. It would probably be easier if we put that 6 over here. Added 6 to both sides. Then, that's a 3 out in front. It would be okay to do that. Oh, you know what? That was silly. I just saw something else that would make this problem a whole lot easier. No, this is correct. But what if, instead of doing it this way, I just divided both sides by 3? These 3's will cancel. 6 divided by 3 is 2. Well, you know what? This is going to be a lot easier than taking x squared plus 9 to the third power. See, that's what logs help us do. They help us make things a little easier. So, phew, glad we caught that before we went through with that. I wasn't excited by that problem. But now I've got this. What do I do? Well, just like last time, if I got a single number over here, I got my base. I know that x squared plus 9 will equal 5 squared. 5 squared is 25. If I subtract 25 from both sides, I get minus 16. X minus 4, x plus 4 equals 0. So we'll put this back over here. X could equal negative 4 or positive 4. Now it seems like we've always got rid of the negatives, right? Always negatives were bad. Well, let's see. If I put a negative 4 into this equation, oh, negative 4 squared is positive 4. And 4 plus 9 is 25. So you know what? That's okay. If I plug in 4, I get the same thing. 4 squared plus 9. Both these answers are okay. Negative 4 can stay. You're allowed. Welcome to the party. All right. Now what do we do here? Now we got a minus 1. That's kind of minus 1's kind of screwing it up because I got to have a log of something. So what do you do? Well, what we can just do is this. I'm going to subtract log base 2 of 1 minus 2y from both sides of this equation. Right? Hold on, the 1 minus 2y. Now these are not like terms, so I can't just put them together. If I'm going to write them, log base 2, 5y plus 2 minus log base 2, 1 minus 2y minus 1. And since I subtract this from itself, I get 0. All right, let's do 2 steps in this next one. I'm going to add 1 to both sides. It's okay if I have a single number over on the other side. I'm okay. But when I subtract, I divide these. So here's how I'm going to write it. Log base 2, 5y plus 2 divided by 1 minus 2y equals 1. Is everybody okay with that? I added 1 to both sides, and since I'm subtracting the logs, I can divide their expressions, their terms. So now I've got a log equaling a whole number, so I can take that base 2 to the first power. So I'm going to rewrite it. 2 to the first power. Now I'm going to solve the equation. So I'm going to flip it over here and do a little solving. I'm going to multiply both sides by 1 minus 2y. Now it's just a linear. Got no squares. So just a little bit of manipulation. 2 times 1 is 2, negative 4y. All right, I'm going to add 4y to both sides. Get 9y plus 2 equals 2. Well, that seems weird. There's only one way for 9y plus 2 to equal 2, and you'll see that in a second. Subtract 2, get 0. Well, it's got to be 0. Now, does 0 work? Right, so I got y equals 0. Does that work? If I plug 0 in here, I get 2. Okay. I plug 0 in here. Ooh, that was a little scary, but 1 minus 0 is positive. So y equals 0 is all right. All right, that's how we use these equations. That's how we solve them. Last one. Oh, jeez. Oh, minus 2. I knew it was too easy. All right. I'm going to try something different this time. We're going to we're going to subtract the c2 minus 1 from both sides. Or c squared minus 1, I should say. So these cancel. I'm left with negative 2 equals. Now these are not like terms. They're close. Well, not close. They have a c and a 1, but the square and the plus, it's always different. So I can't combine them, but I can write them the way we've got it. Minus log base 10 of c squared minus 1. Right. When I subtract logs, it's very crooked. It's annoying me. There we go. I can divide. I get c plus 1 over c squared minus 1. And here I am. Here's my base. Here's my singleton number. So it's 10 to the negative 2 equals c plus 1 over c squared minus 1. Now how do we solve this one? Scoot it down just to make it one more line here. Now 10 squared is 100. But what's that negative do? It puts it in the bottom. Alright, so let's jump it over here. I'm going to cross multiply. Basically, I'm multiplying both sides by 100, and I'm multiplying both sides by c squared minus 1. So I get c squared minus 1 equals 100 times c plus 1. 100 seems like a big number. Let's see what's going on. I know it's a quadratic, so it's going to stay. I'm going to distribute that through. Now I got to set it equal to 0. So I'm going to subtract 100c from both sides. I'm going to subtract 100 from both sides. Well, it's not really that bad. If I've got 101, I need to get 100. Well, that's really weird, but doesn't this work? Isn't negative 101 times 1 negative 101, and negative 101 plus 1 is negative 100? It does. So my two potential answers would be, I'll put it down here. C equals 101 or negative 1. All right, let's see which ones work. All right, let's try 101. 101 squared minus 1, that's definitely a positive number. Okay, now what about the negative 1? Negative 1 squared is 1. 1 minus 1 is 0. Oh, negative 1 plus 1 is 0. Remember, it can't equal 0. It's got to be a positive number in there. It's got to be. So I'm sorry, negative 1. You don't get to play. Because if you did, you would destroy everything. That's how they work. That's how you solve these types of logarithmic equations. Now this is going to set us up for something really awesome in the future. Well, in the future, it's not going to be very long. All right, another application of logarithms are a scale, a Richter scale. So a Richter scale is really a scale that looks kind of like this. And what you have is you've got things like this. You've got 0, 1, 2, whoops, 3. Almost wrote something different. I better erase that and try that again. 3, 4, 5. Looks like a typical linear scale, doesn't it? But it's a logarithmic scale because what it really means is 10 to the 0, 10 to the first, 10 to the second, 10 to the third, 10 to the fourth, 10 to the fifth. That's what this means. So if we had a scale that was registered 3.2, and we had one that was registered at 4.5, you think, oh, that's only one magnitude more. It's only a little bit more, not big deal. But it is, because it's all based on a power of 10. So if this scale was true, I mean, we'd have 0 to 10, then 100 would be way over here, and 1,000 would be way over here. We'll just keep getting larger and larger and larger. But here's the answer to the question. We take 4.5, we subtract 3.2, what do we get? We get 1.3. So you think, oh, is it 1.3 times larger? No. It's 10 to the 1.3. Okay. Now that's a pretty big number. Well, is it a big number? Let's find out. 10 raised to the 1.3. It would actually be about 19. It says about how many times? Well, it's about 19.6 times greater. Yikes. So, that's a big deal. That's a big deal. So if you go from 10 to the first, which is 10, 10 squared, which is 100, one magnitude of jump on a Richter scale is 10 times greater. Okay. So because this is more than 1, it's more than 10 times greater. That's how Richter scales work. They're based on a logarithmic scale. There's other scales that are involved with that too, but that's the one we're going to look at for now. Decibels and sound levels are also done with a logarithmic scale. So they're used quite often. All right, that's what we got for today. So I hope you guys have a great one. You're doing a great job. Keep it up, and I'll see you later.